Right. I think a good starting point for this talk is to get back to the what is called the Lorenz Attractor. It is a reduced version of the atmospheric attractor, which is in many million dimensions. It's a reduction to 3 dimensions of this attractor, and it shows, actually, it illustrates quite nicely, I think, from the very start, what the difference is between weather forecasting and climate forecasting. I'm going to start, well, try to start an animation here. I found this animation on YouTube, and I found it extremely efficient to convey the idea of what actually is weather and what is climate. You see at the start of the animation here, you see a line, but actually there are points that are very close to each other, and they are moving along the path, their own path, on the attractor. The attractor is what actually keeps them on certain tracks, and that's you can see that as climate. And you can see that these points that were very close to one another start diverging quite a lot. They are now quite far apart from each other, at least on a big chunk of the line. Now they are coming back together. They will come gradually again closer to one another, with some points actually being further away. So you start seeing already that there is some kind of separation between the points. Then we go again for another round. And you can see already a second line there on the northern part of the attractor. So some points get really separated from the main group. And here we go again, another round. Actually, what this animation is showing is that these points, it can take a while, but in the end, ultimately, they will all be very far apart from each other. Why? Because they were not exactly at the same position as their neighbors. They were at a slightly different position at best. Each point actually can be viewed as a weather situation in the phase space. Here, a reduction to 3 dimensions. And it just means that with weather forecasting, if you want to forecast weather, if you do not know the initial conditions in a perfect way, you just can't. Sooner or later you will diverge from the real weather if you want to simulate it. You need actually to need your initial conditions perfectly, which is not the case in reality. So accurate weather forecasts have a strong limitation. You cannot go beyond a few days, and sometimes if you are lucky, 1 or 2 weeks. But in the end, your forecast will get wrong. This is not the case for the attractor, though. You can see the points there completely, away from each other. Right. So my point is that trajectories, the individual trajectories, they will end up diverging far apart from each other. The climate, actually, which is this kind of butterfly, this beautiful shape, this is what you want to try and predict using a climate model. And this is not the points that you want to predict, it's actually the parameter here from this set of differential equation rho. And to do that, you launch many points, you simulate many of those points. And as you've seen on the animation, then you start having this picture of this butterfly materializing, and you can derive your climate from those many simulations. So I'm going to start with the techniques and the models that I use for weather forecasts, because anyway, for seasonal forecasting and for climate forecasting, the models themselves are not too different. So I'm going to show you a bit the kind of the principles, the anatomy of a model, and how an operational forecast is produced, taking the ECMWF model as an example. So what it comes down to, what we want to do is, in fact, calculate the weather. And this is not a new idea. It was already in some people's minds. For example, Louis Fry Richardson in the 20s, he has this idea of a big orchestra with people having their slide rules and calculators, and with some coordinators and conductors in the center, telling each member of that orchestra to, where and how they have to perform these calculations. Of course, it was far too slow to keep pace with the weather, and also there were a lot of, it was a methodology prone to human errors. What one had before the advent of powerful computers and numerical techniques was more models of a qualitative nature, like the model of the Bergen School. And it's a model that is still very influential today, but I mean, this is basically a qualitative model. It's only in the 50s that the first numerical integrations were really starting to get momentum, and it was then, from then on, accepted that it was possible to calculate, to produce simulations of weather. Of course, the simulation of weather is very demanding computationally. So we are talking now actually for not really for weather, but certainly for seasonal and climate, from a move from peta to hexa computing. This is, well, I give you as an illustration Moore's law that says that computer performance doubles every 18 months. This law is still valid. This is an example of Richardson's slide rule orchestra I was talking about. You can see all these people that are trying to calculate variables like wind, temperature, pressure, with their slide rules and calculators, and in the center a column with people kind of coordinating all the calculations performed by this orchestra, pointing with a beam where the calculation has to be done. Now, maybe the first source of uncertainty we could talk about is the fact that models are trying to describe objectively how the atmosphere works. And to do that, they solve complicated equations. And to do this, to solve those equations, you need actually to discretize. You cannot solve these equations analytically. So there already you start diverging from the reality. You are working in a discretized world. The simulation is carried out step by step. I think it's still 12 minutes on the ECMWF operational prediction model. And typical models will use a three-dimensional grid. The ECMWF is a bit more complicated because you use spectral methods, but you can consider it's equivalent to working on a three-dimensional grid. Those spectral methods are actually a bit more efficient, so that's why they use that. And that simulation starts from initial conditions, which is called an analysis, which is estimated from observations, of course. Very important to have observations. It's a link to the real world. And previous forecasts that actually are very, very handy because the data coverage of observation is not homogeneous, and there are many places where those observations are lacking. They are not always reliable either, so you must have a basis to reject them if they start doing funny things. And a comparison with the previous forecast, saying, you know, to check if the observation gives reasonable values is necessary. Of course, these operations, this calculation, stepwise integrations of the model demands a very large number of calculations, and that's where you have those errors growing gradually. This is an illustration of a web, of a grid, sorry, three-dimensional grid in height, in latitude and longitude, where the equations will be solved. And the forecast will actually, you can divide the forecast in 3 different steps. You have the step where you gather the observations. These are coming from the real world, and you have to then ingest them into the model, and then you go from the real world into the model space through a process called data assimilation. This is a first source in this process of uncertainty. Then from the analysis you start producing a simulation, another source of uncertainty, where, as I just told you, the errors will start growing. And then from the simulation, you derive a forecast. But to be useful, the forecast has to be translated from model space into the real world. And you use methods like downscaling or post-processing to achieve that. Again, another source of uncertainty. They can make the forecast more accurate in some respects, but there is always a trade-off. We'll see that later. So the observations, yes, they call from, in a model like the ECMWF operational model. They come from all over the place. You get what you can see is that land is much better covered in general than oceans. There are observations from the surface, observations from upper levels. There are conventional measurements, so with manned or automatic stations at the surface or in airplanes, for example. And there are also teledetection instruments, teledetection observations that are provided by satellites, wind profilers, etc. These teledetection measurements actually are more uncertain than conventional measurements, and what is typical is to calibrate or to correct these teledetection measurements using conventional observations. Here are some examples. This is a snapshot of the coverage of data at on the 27th of September 2004, 12 UTC. There are 4 analysis cycles, so this is the main one actually where the main forecast is produced. Here on the left you see SYNOP data coverage, SYNOP ships. These type of observations, you know, have very good quality. So you can see that 70 to 90% of them are used. The problem is the coverage. You can see that land masses, some land masses over Africa are not covered, but in general, the continents are fairly well covered. On the other hand, the oceans are much less. This is partly compensated by the buoy coverage. So you've got drifters, drifting buoys, so you've got moored buoys there. You can see that many of them are used as well, good quality stuff. Upper air data, then you have 70% of them used, very good data, and used to calibrate satellite data from, for example, to get some radiance information from some slices of the atmosphere. Pilots profiler data, so this is a kind of measurement of wind. Profiler is teledetection, is kind of is to be compared to radar techniques. Aircraft data, again, you have some areas where we have a lot of them, but not everywhere. Satellite data from geostationary here goes Meteosat, and then you've got polar satellite data. You can see that with satellite data you have much less data use. You have many more data, much more data, but you don't have a large proportion of them being used. Very useful in data space area, of course, more particularly the southern hemisphere. So the process of combining these observations with to feed the model with this observation and combining it with the background or the model is called the data assimilation, and the analysis that is being used there is called 4D VAR, four-dimensional variational analysis. And what you do is try and find the best compromise. If you look at this schematic here, you have the observations in green. You have an assimilation window about a main analysis time. Here, cycle is 12Z, 12 UTC. And you can see that the observations, this is in blue, this is the model, the previous model forecast. This is actually what is called also a background or first guess. But in the light of this data, when this data arrive, the previous forecast is being corrected, is being amended to get a better fit with the observations. So it's a kind of compromise in space and in time, hence the 4 dimensions. And of course, this data, as has been said several times today, is not perfect. There are issues, and the analysis scheme is trying to reject the bad data, the data that is not realistic, or this, as I said, or that is very different from model background. And also data that is not consistent with neighboring observations. So in the analysis scheme, there are all sorts of routines that check on that in order to get rid of as much as possible of bad data. There are also blacklists to put data that is systematically bad out of action. So this is put on the temporary blacklist. So the data is monitored. If it behaves badly, it is put on the blacklist. But if it behaves better, after a while, it may come back on and be accepted as input to the analysis. There are also permanent blacklists where some data is put systematically, data that is unknown, new satellites, for example, new platforms, just to assess them. And also some data that doesn't need to be used because it's redundant. So as I said, there were 4 analysis cycles. There are 4 analysis cycles, and the main cycles at 0 and 12 UTC. And why are they the main cycles? Because they are the starting point of the main operational forecast. You get a better data coverage at those cycles. Something that is very important to repeat and repeat and repeat is that analyses are never perfect, and far from that. And why is because first you have to compromise. There are areas where you won't have any data, and you will have to use your model to make some guesses. about the most likely value of your parameters or variables. But data can also be accepted by the analysis scheme. It's not guaranteed that bad data is going to be kicked out. Also, good data may influence the analysis in the wrong way. A point I want to know as well on this, that increased uncertainty is that an analysis error is not necessarily leading to a bad forecast. It's not that simple. So the integration of the model, this is for illustration, the 6 primitive equations on which the model is based. And these can't be solved analytically, so you have to go through to discretize them. And as I explained earlier, this is a source of errors. Discretization of the model, I showed earlier a kind of 3-dimensional grid. So what you see here in the ECMWF model are the levels, so the vertical grid of the model. And at the moment there are 91 levels. Tomorrow they will start running their models with 137 levels, so a substantial increase of levels. And this starts from 10 meters above the surface to around 80 kilometers. This is ETA, hybrid coordinate system, so it is very close to the surface in the lowest layers, and it follows pressure surfaces in the top layers. I forgot to mention, there are also layers, extra layers in the soil. Discretization, horizontal discretization, so the discretization resolution, sorry. The current resolution is around 16 kilometers, and this is because the model actually works with, as I say, spectral method with spectral method that use 1,279 spherical harmonics. This is quite a lot for a global model. And you can see here a picture of the model, the equivalent near surface on a reduced Gaussian grid, which gives you the resolution you achieve. So it's quite good. Nevertheless, what you get, you can try and be as precise as you can. You are never going to be exactly like in reality. And on this picture, you can see that you can walk from Scotland to Ireland. The orography and the land-sea mass are different in the model than in reality. A major source of uncertainty is the parameterization of subgrid physical processes. Just because we are having a grid, we work with a grid, and the resolution of the model is limited to 16 kilometers. There are many processes that are taking place below the resolution of the boxes of the grid. And in order to try and take account of these, you cannot simulate them explicitly since they are smaller. They work at a smaller scale than your grid. But you have to take account of that using what is called parameterization techniques. So these parameterization techniques are also equations and sometimes very sophisticated, but they are often based on empirical knowledge as well. It's not only on theory. And some of the processes that need to be parameterized, land surface, turbulent exchanges near the surface, radiative transfers, cloud physics, thunderstorms. In a hydrostatic model like ECMWF, when I showed you the equations earlier, actually it showed that the ECMWF model is still a hydrostatic model. It means that it considered the atmosphere in balance vertically. This is something that you can do so long as you are fairly coarse in your grid. But if you start increasing the resolution, then you have to be able to resolve convection, thunderstorms, and in that case you have to go as in what they call a non-hydrostatic mode. They are working on it now, but they are not there yet. So thunderstorms in the model, ECMWF models, are not resolved explicitly. Again, a source of uncertainty. When you downscale the forecast, what you do is translate it back from the model, grid points, levels, model orography, to the real world. For example, a weather station, or a power plant, or whatever. And to do that, you use post-processing methods. I named 3 here that are the most widely known: is perfect prog, model output statistics, and the Kalman filter. As I said earlier, these methods will have a purpose, increase the accuracy of the forecast. But the price to pay is you may lose at detecting, when you want to detect extreme events, because, for example, model output statistics will be based on, we'll say, the model's usual behavior. But when an extreme event occurs, of course, the statistics from this post-processing will bias the value given, the final value, towards a more normal, a less extreme value. For the Kalman filter, is more or less the same. It adapts itself to the most recent past, but when there is a sudden weather change, then you can, your Kalman filter can put you in trouble. Again, source of uncertainty. So the reliability of weather forecasts, I think unfortunately, we haven't got much time to dwell on this, but I think we can say generally that it depends on several factors. And the atmospheric flow regime, there are situations, anticyclonic situations that, for example, that are really stable. You can have when a very active storm track with a lot of lows passing, and then the prediction of each individual feature in the storm track may be more tricky. The season forecast errors grow and propagate more quickly in winter. And also, that is well known that precipitation are harder to predict in summer than winter. And the reason for that is that in summer, precipitation is dominated by more convective events, and convections, as I just said, are like thunderstorms and showers, are not resolved explicitly, or they are not resolved so well anyway than larger scale weather systems. The location as well, of course, Europe is more volatile than the subtropics. The scale of the features you want to predict matters. If you want, again, a small scale phenomenon, it depends very much on the resolution of your system, and you'll generally be better if you want to predict, fronts of a low of a fairly good size. So I would say that a small scale, transient small scale phenomena are much harder than the synoptic scale phenomena. The variable you want to predict as well matters. If we have time, I can show some statistics, but in general, what I can say is that temperature is one of the easiest variables to predict, despite the error sometimes. And the main reason is that it's associated with the larger scale features in general. Wind is much more volatile because it is associated with much smaller features. You can, even if you don't make large errors, you can really lose track of the, try and predict the variability of the wind precisely even on the same day or the day after. You have much better correlations if you, with temperatures. Precipitation is a very complex process to simulate, so it varies with the type of precipitation. You can have convective precipitation, precipitation associated with large weather systems. Also, the topography matters a lot. Everyone knows that it rains harder in mountains than on plains. Surface, the sun radiation that reaches the surface, also trying to we've looked at irradiance and these things, but it's extremely volatile and dependent on cloud cover, and this is maybe bad news for the energy sector, but it is like this, so one can try and improve things, and that's going to happen because there is demand for that, but it is very, very hard to predict. The weather forecasts themselves, from what we saw at the beginning, is you can say 1 or 2 days in the short range, you'll be all right. You can most of the time have very good predictions of the synoptic scale. It means I mean by that storms and cold fronts and these features. If you want to predict thunderstorms, it becomes very tricky, even hours ahead. So in the nowcasting range. In the medium range, actually, officially it starts at day 3. Sometimes at day 3 you get pretty good predictability. Sometimes even at 2 days it starts degrading. But in general, anyway, what's going to happen is that the errors in the simulation grow. They quickly and they begin really to overcome and contaminate the forecast and overcome the whole scene. And if you use a high resolution model, it's going to get worse. So if you have a coarser model, it will protect you a little bit from error contaminations. But in any case, after a few days, your forecast gets wrong. And because of that, a probabilistic ensemble approach becomes necessary in view of the growing uncertainties, the growing errors. And so one will take more an approach, a statistical approach with distributions, looking at different outcomes, confidence intervals, and all these things. So we've seen that the analysis, no analysis is perfect. We have the fact that we can't escape to that is that the initial state of the atmosphere is known only approximately. We have an incomplete data coverage, instrument errors, assimilation not infallible, and also the model is a simplified approximation of the atmosphere. We work on grids and discretized model, and not all physical processes can be explicitly described in the model. And all this gives way to substantial uncertainties, more particularly in the initial conditions, which are crucial, as you've seen at the beginning, for weather forecasting. You want really to predict as accurately as possible where this point will be in the next day, 2 days, 3 days, etc. And the technique applied then is ensemble forecasting. And the idea is to run a set of forecasts, each starting from conditions that sample uncertainties about the initial state of the atmosphere. And you run a set of different models if you want to build up what's called a multi-model ensemble to take account of the uncertainty inherent to the model formulation. This is more, I think, it is done in weather forecasting as well, but it is more the case in climate. and in climate and seasonal forecasting, because the model formulation is a larger source of uncertainty than in weather forecasting. The ECMWF Ensemble for weather forecasting has 51 forecasts, 1 unperturbed control and 50 perturbed forecasts. It's a global spectral model like the one we've just seen, but at half the resolution, broadly speaking, and with only 62 levels. It's also run twice a day, 0 and 12. And it is also, the analysis is performed through 4D VAR. The initial perturbations are achieved using a technique called ensemble data assimilation and singular vectors. The principle actually is of ensemble data assimilation is to perturb, to generate a set of different analyses by perturbing observation and sea surface temperatures slightly at the beginning, and then run an analysis on that. I think at the current configuration there will be 10 of these analyses being generated. And what you obtain then is a collection of different analyses that take account of the uncertainties in the analysis, the starting analysis due to the model formulation and the physics, etc., the parameterization, and the observations as well. So it samples the analysis uncertainties. This is what the very start. So you've got you haven't started your forecast yet, and on top of these perturbed analysis, you add singular vectors, and these are actually these are the fastest growing modes over a period of 48 hours. So you identify these fastest growing modes of disturbances, initial disturbances in the first 48 hours, and you add them to these analyses obtained through EDA. So you have a combined set of EDA analyses and singular vectors, and you produce your 50 initial perturbations. It's, of course, needless to say, computationally very demanding, but this is actually now thought as being the best way to assess the initial uncertainties in the forecast. There are other methods that have been used as well. Monte Carlo, completely random. It's not very efficient because why should you perturb in areas where I mean, it won't make any difference. So completely random approach is not really efficient. The American have been using the breeding vectors, so it's just looking at different analyses and forecasts, look at where the errors have been consistently growing, rescaling them, do that several times, and then keep the errors that come consistently all the time, that are organized dynamically, use them as starting perturbations. Another one here being used by the Metofis is ensemble Kalman filter. What you get then to assess forecast uncertainty are, you can look at, for example, the ensemble mean, which is a kind of consensus. So where, in general, you can consider that as the forecast from which you are least likely to depart in your observation later. The ensemble spread, which gives you an estimate if your ensemble is well calibrated, is good, then it will pinpoint regions of high and low uncertainty. Clusters that will give you a kind of that will group similar scenarios and highlight multimodality in the model, in the forecast. Sorry. Also, you can, of course, build up, make probability maps that are going to, you look at some event you are interested in, and you look at the proportion of forecasts that produce that event. To do like this with only 51 members is a bit crude, but that's an approach. You also can build some indices like the Extreme Forecast Index that gives you actually the potential for extreme weather. What it does, actually, the principle is that it measures the distance between your ensemble distribution of all your 51 forecasts and the climate distribution. And a value of 0 means that you have absolutely no extreme. Your climate, your distribution in the EPS is of the ensemble is very similar to the climate distribution. 0 means equal distribution of the ensemble equals the climate distribution. When it's plus or minus 1, then it means that your ensemble predicts record-breaking values. Now, if you move on beyond the medium range, well, what you've seen here is an ensemble approach to assess uncertainties in the initial conditions because these are the ones that matter for weather forecasting. Here, we move a bit away from the importance of initial conditions in the simulations for simulations for the simulation of weather, but something else is coming up. It's still actually something that depends from initial conditions, but not from the atmospheric state, rather from the ocean. So we have, when we move beyond 2 weeks, you will get the initial conditions in the atmosphere themselves are becoming less relevant. There is some kind of memory loss of the initial state. And if you have an atmospheric model and you let it go like that for a few weeks, it will not produce forecasts that are more skillful than just using climatology. However, there are some forcings, persistent forcings, that can actually direct or kind of push your forecast in some directions. For example, patterns of temperature anomalies in the Atlantic. Everyone has heard of the NAO here, I guess. And tropical Pacific, El Niño, La Niña. The extent of snow cover over Eurasia. These are permanent forcing on your forecast, that on your weather, that may direct and may try and push it to some direction: cold weather, warm weather, loss of rain, etc. But on average, not something for a day, not for. We're not trying to predict the weather anymore. It's just average conditions over a certain period. But so what I'm saying here is that there may be some predictability of average weather conditions that can be gained from exploiting these forcings. And this is basically why when one goes beyond 2 weeks, one couples the atmospheric models to an ocean model. I make a quick comparison here. In the short range, you've got for weather forecasting, you can try and predict transient weather systems, storms, front, anticyclones with some predictability. When you go in the longer range, beyond 2 weeks, seasonal, etc., these systems are no longer really predictable. You can simulate one. If your model is good, it will simulate some, but they won't be at the right time, the right position. Forecasts in the short range are able to pick up day-to-day variability of weather variables like temperature, pressure, wind speed, etc. In the long range forecasts, you are going to try and predict overall average conditions, range of possible outcomes, certainly not definite weather pattern. In the short range, you can use deterministic methods, so use one single forecast, or probabilistic, no problem with that. But when you go into a longer range, you can't do otherwise. You have to look at the probabilities because the uncertainties are growing so much. And since you are coupling in the long range, you are coupling your atmospheric model to an ocean model. Here, initial condition of the ocean itself becomes crucial. If the atmosphere loses memory of its initial state, it's still an initial value problem, because you couple the ocean that has more predictability and it is very sensitive. A good, accurate prediction of the ocean pattern is dependent on an accurate description of the initial state. In the short range, you don't bother about ocean. Actually, your SST fields are fixed. You don't move any others. It's just the atmosphere that moves, and the rest is fixed, or you can consider as nearly fixed. Also, in the short range, I think it's an issue in verifications. This is my job. For weather forecasts, you get lots of sets of forecasts, lots of observations, and you can do nice and a lot of verification, and nice and very verification you can trust, really. With longer range, because the models actually are run less often, you have less data as well to check them. So the quality assessment is sometimes a bit more problematic. You can have some views, you can use some methods, but there is more uncertainty as to quality assessment as well, due to the nature of the problem. Now moving on to seasonal forecasting. It's, as I said, it's still an initial value problem. The initial state of the ocean is important. It is a global exercise. The resolution is coarser than for an atmospheric model. We couple ocean and atmosphere, so because much of the predictable signal comes from the ocean. And we take an ensemble approach, and preferably a multimodal approach like EuroSIP, also the National Multimodal Ensemble in the US, or in APEC. Here in this case, you achieve initial perturbations by starting each run from different dates. So it's nothing to do with singular vectors or EDA. Some current issues is the disappointing skill over Europe. And also a lot of work is being done to improve uncertainties due to some deficiencies in the model, like the SST, one needs a better resolution, more particularly to resolve the sharper meridional gradients of sea surface temperatures. We have also difficulties to reproduce the Madden-Julian oscillation realistically. It's an oscillation in the tropics, for those who don't know, so associated with precipitation in the tropics, and it has repercussions over Europe. And the model don't tend to simulate it too slow, or sometimes it will stall on the maritime continent. It's not satisfactory still now. The difficulties to reproduce the quasi-biennial oscillation is also an oscillation there in the stratosphere, in the equatorial winds in the stratosphere. And it has also an impact over Europe through weakening the polar vortex, which may actually, by weakening the polar vortex, you can increase the probability of cold events. So it's important to get this right. The problem with the QBO, with this oscillation, is that it is not persist long enough in the models. So we need a better, I'll just go a bit more quickly here in the list, a better resolution that is needed in the stratosphere. The Metophysics have just done this, I think, in their model, to get a better downward propagation of teleconnections and simulate better sudden stratospheric warmings. So a better initialization also is needed. It's still not, I mean, this still needs to be improved, and also the modeling of Arctic ice and aerosols must be improved as well. About climate prediction, this is not an initial value problem anymore. Now you don't care really of how what were the conditions when your forecast started. On the contrary, what is being done is to spin up the model until it has forgotten its initial state. before starting the actual climate simulation. We are now facing a boundary value problem, so we have actually all sorts of different kinds of forcing that are going to make your forecast, your simulation evolve in one or other direction. Also, of course, resolution, and you need downscaling techniques for regional applications. For example, you can use nested grids or weather generators. Also, assessing the extreme weather in a changing climate is a problem. Models are in general not too good for extremes, but climate prediction really needs something extra to assess that. Larger uncertainties in the models, specification of forcing and feedback. So you have actually, whereas in weather forecasting, your largest uncertainties reside in the initial conditions. In a climate prediction model, your largest uncertainties will be really things like anthropogenic forcings, which rely on some sorts of scenarios about economics and social evolutions of the world, the availability of fossil fuel reserves, etc. Substantial, very extremely big amount of uncertainty there. Some natural forcings are also very uncertain, by the way, volcanic activity, so we can't say long in advance whether a volcano is going to erupt, but it may have a major impact on the evolution of the climate. Or your seasonal forecast as well, by the way. So the effect of aerosols, the clouds, all these actually have quite a high level of uncertainty. Also, the fact that feedbacks from the same forcing can produce opposite feedbacks. You know, things like increasing temperature, more moisture means more clouds, so lower temperatures, or it means more water vapor, which means more heat. So these are two possible kind of opposite feedbacks. And of course, what you have to do is take a multimodal approach. The conclusion here is that we've seen that the atmosphere is inherently chaotic, and so there is some limitation to weather predictability. So when you want to predict weather, you are sensitive to initial conditions, and you will never get them perfect. So forget it if you want to predict the weather in a year's time. This does not mean that climate forecasts are not feasible. They are not sensitive to initial, but more to boundary conditions. There are many uncertainties due to incomplete knowledge of the initial state in weather and seasonal forecasts, and also incomplete knowledge of forcings in climate forecasts. Model formulation, the parameterizations, for example, are also a large source of uncertainties. Discretization and truncation, which are associated with the numerical techniques used to solve the equations and the resolution of the model. Ensemble prediction offers a good tool to quantify uncertainties on the initial state, forcings and model formulation. That's all good, but now what about the energy sector? Because I haven't talked about it at all. In fact, in the energy sector, many systems exploit weather information as input, and they take only deterministic forecasts. So even if you have a probabilistic forecast, it has to be transformed into some deterministic yes or no forecast. It must be said that fitting probabilistic weather information directly into a demand-supply model is not that straightforward. It's very hard and not necessarily efficient. We should maybe move to a more probabilistic treatment of treatment downstream that is very close to decision point, actually. And from weather information produce a probabilistic demand-supply model. That's it.